You know, everything around us, from the music we stream to the data zipping to our phones, it's all just signals. But how do you actually describe them with math? Well, the secret is to start small, with the absolute most basic building blocks of any signal you can imagine.
Think about it for a second. What's actually happening when you flip a light switch from off to on? Or when you tap a key on your keyboard for just a split second? These aren't just little physical things we do, they're signals. And it turns out, the math to describe them, and even much, much more complex signals, is surprisingly simple.
And that's really the core idea here. We're not going to try to understand a whole symphony all at once. Nope. First, we need to learn the individual notes. We're going to use two incredibly simple, powerful tools, our building blocks, to construct something far more interesting.
Okay, let's get into it. Our two fundamental building blocks are called the unit step and the unit impulse. You can just think of them as the mathematical version of a permanent on switch and an instantaneous tap.
So, first up is the unit step, which we write as U of t. Just picture a timeline where, for all of history, the value is just 0. Nothing is happening. Then, right at the exact moment of time 0, bam, it instantly jumps up to a value of 1 and just stays there forever. It is the purest turn-on signal you can possibly have.
Our second block is the unit impulse, sometimes called the delta function or delta of t. Now, this one's different. It's 0 everywhere, for all time, except for one single, infinitesimally brief moment right at time 0. And in that moment, it spikes with infinite strength. The best way to think of it is like a perfect, instantaneous tap, like a single strike of a tiny, infinitely powerful hammer.
Seeing them side by side really makes the difference pop. The step function, that's a permanent change. It's a switch that flips on and stays on forever. It has an infinite duration. The impulse is the total opposite. It's an event that happens in literally 0 time, and then it's gone. One is a state of being, and the other is a single event.
So now we have our two blocks, a permanent on switch and an instant tap. But that's a little bit limiting, right? What if we want the switch to flip at a different time? Or what if we want it to be stronger or weaker? Well, that's where transformations come into play.
We can basically customize our blocks in 3 key ways. First, there's scaling, which just changes the height or the amplitude. So instead of jumping to 1, maybe it jumps to 5 or even -3. Second, we've got shifting, which lets us slide the whole function along the timeline. That way our event doesn't always have to happen right at time 0. And third, we can do something called reversing, which creates a perfect mirror image of the signal.
All right, let's put this into practice and try to figure out a trickier example. Now, this function, -3 u of 1 minus t, it might look a little intimidating at first glance. But trust me, we can break it down logically using those 3 simple transformations we just talked about.
Okay, let's just walk through this one together. First step, find the starting point. The trick is to always set whatever is inside the parentheses equal to 0. So 1 minus t equals 0. That means t equals 1. Easy enough. So our big event happens at t equals 1. Second, let's figure out the direction. See that little negative sign in front of the t? That minus t tells us the whole function is time reversed. A normal step function would be off before 1 and on after. But this one's a mirror image. It's on for all time before t equals 1. Finally, the height. That -3 out front, that just scales it. So when the signal is on, its value is -3. And that's it. We've cracked it.
So, we can describe a switch that turns on and stays on forever. That's cool. But what about a signal that turns on, stays on for a little while, and then turns off? Now this is the aha moment. This is where we combine our simple blocks to create something genuinely new and incredibly useful.
Okay, so here's the really cool part. We can create a signal that has both a beginning and an end. This is basically the foundation of all digital information. Not infinite states, but these discrete, finite pulses. And the amazing part is, we can build one just by adding and subtracting our simple step function.
Here it is. This is the function we're going to build. I know it might look a little weird, subtracting one function from another, but let's break it down piece by piece and see exactly how it works. Our first building block here is 2u of t minus 1. The t minus 1 part shifts the whole thing so it starts at t equals 1, and the 2 out front scales it so it has a height of 2.
So at time equals 1, our signal jumps from 0 up to 2 and just stays there. That's our on switch. Now for the really clever part. Our second block is negative 2u of t minus 3. You can think of this as an anti-step. It's a step function that starts at t equals 3, but it has a height of negative 2. So at t equals 3, it's going to introduce a value of negative 2, and that's what's going to act as our off switch.
So what happens when we add them together? Well, before time equals 1, everything is 0. Then at time 1, that first function kicks in, and our signal jumps up to a value of 2. It stays at 2 until we get to time equals 3. That's when the second function activates, adding a value of negative 2 to our signal. And what's 2 plus negative 2? It's 0. The signal snaps right back down to 0 and stays there forever. Just like that, we've created a perfect rectangular pulse.
Okay, this is a neat math trick, for sure. But why does any of this actually matter? Why should we care about building these abstract shapes? Well, because these simple blocks are literally the language we use to describe and interact with the physical world.
You know, one textbook on this topic puts it perfectly. It says that these functions are essential for modeling and predicting the behavior of a dynamic system. This isn't just some abstract theory. It's a fundamental tool that engineers and scientists use every single day.
And the applications are absolutely everywhere. That rectangular pulse we just built, that could be a single bit of data in a computer. That impulse function, that's how engineers can model a building's response to a sudden earthquake, or how a circuit reacts to a power surge. These concepts are totally foundational in control systems, in signal processing, and even for really advanced tools like the Laplace transform.
And that really brings us to a final thought. We started with just a simple switch and a tap. We then combined them to build a finite pulse. So if these are the basic Lego bricks of signal analysis, just stop and imagine the complex and beautiful structures, everything from your favorite song to medical scans, that we can now start to build and understand, all starting from right here.